I'm delighted to welcome our next speaker to the stage. Dimitra Panagou will tell us about reliable and resilient multi-robot systems. And Dimitra is an associate professor in the Department of Aerospace Engineering at the University of Michigan. She got her PhD in mechanical engineering from the University of Athens in 2012. And since then, she was a postdoc at the University of Illinois. She was also a visiting scientist at the University of Pennsylvania. And eventually, she joined the University of Michigan. She has a lot of awards that show the community's recognition of her work. And so in particular, I would like to highlight the NASA Early Career Award, the AFOSR Young Investigator Award, and the NSF Career Award. Dimitra, I really look forward to hearing about how to make swarms reliable and resilient. So please take it away. Let's give her a warm welcome.
Thank you very much, Daniela, for this very kind introduction, and thanks to organizers for inviting me to give this keynote. So I will try to give you a very high-level description of some of the problems that we have been working along with my students in the recent years that are related to reliable and resilient multi-robot systems. Our ultimate goal and vision is to enable multi-robot systems to perform autonomous operations in a diverse set of environments and applications. And in particular, we want them to do that in a reliable way. And in this context, with reliability, I mean that we would like the robots to behave safely, not cause harm, and make those decisions, make their decisions on how to move around in a secure manner, meaning that they are able to reconstruct trustworthy information in order to make those decisions, and also do that in an efficient manner, meaning that they are able to satisfy the desired level of performance for their mission. Which brings me also to the next requirement for this vision, which is related to the property of resilience, meaning that we would like the systems to be able to operate even at a minimum or at a reduced capacity when bad things happen, which could be anything from a natural disaster to a malicious attack. So in that context, resilience is the notion of robustness. You don't want your system to collapse. You want to be able to detect and monitor and recover from undesired effects. And also adaptability. You would like to be able to restore the nominal functionality or adapt to the new environmental conditions. And so one would ask, is it easy to enable this type of resilient and reliable systems? Where are we and what makes the problem difficult? If we were to start looking into a rather simple architecture and a simplified version of the problems, you would start with your multi-robot system being represented typically as a graph in an abstract level, which is trying to capture the entities that are available in your multi-robot system, which could be nominal and adversarial nodes or robots in different teams and different objectives, capturing also the interconnections and the information flow between them, subject to various constraints because of the environment and the different objectives that they have to satisfy. And what do you want to do with this multi-robot system? Well, you need to design safety controllers using information that needs to be trustworthy, needs to be reconstructed in a secure way, that needs to flow over a secure communication network so that you are able to reconstruct those efficiently. And all that in the presence of cyber adversaries and possibly physical adversaries that they might want to degrade your nominal mission. And so this is a problem that has been well studied in our community and the controls community, and it's now well known that in the presence of a nominal, when everything is nice and things are collaborative and agents are sharing all their information, then you can have collective behaviors and formations and swarming behaviors and so on. But even in the presence of one single robot that does not behave according to the nominal protocol any longer could have the effect of really breaking the nominal mission. In this case, is that the formation was able to be disrupted. So in the next couple of minutes, I'll show you some very high-level results that we have developed over the years on network resilience against this type of cyber adversaries. So what I mean with cyber adversaries, let's discuss what is the malicious or threat model. Well, the idea is that you have some agents in your network that for whatever reason, they stop playing the nominal protocol. It could be intentional, it could be just a fault. And or they do not share their correct information with the rest of their in-neighbors. So the question here is how you can make sure that you can tolerate this type of behaviors, and in general, these type of problems are very hard to solve. The combinatorial notion of how should I construct my network so that I'm able to tolerate this type of effects is really an NP-hard problem. But a key takeaway message is that if you simplify the problem by putting some structure on the communication network, some structure on the communication graph, and you design properly the information filtering algorithms, the way that the agents are processing their information, then this can lead to sufficient conditions for network robustness. And so one method for that would be to consider specific communication structures on how you're structuring your robots in a leader-follower. We have a leader-follower paradigm here. And if you do so, then, and you play specific information propagation algorithms, which I'm not going to get into the detail right now, the idea is that you can have conditions that will give you resilience from the perspective of if every agent is capable of receiving messages that are identical from at least one given number of incoming connections, then this provides a guarantee on resilience, that it's capable of filtering out the bad information and only recovering the correct information. So the key takeaway message here is that the number of connections that you are allowing your network to have is directly related to the number of adversaries that you can tolerate. Which means that if you want to make a network that is being resilient, this is a simulation case study that shows that here we have a network where we have one adversarial leader that is sending to the formation a reference trajectory that is rather unsafe for the formation, so because it would make it crash to the wall. But because our network has this topological structure for its communication topology, and it plays this resilient protocol for the information propagation, it is capable of filtering out this bad effect and moving safely around the environment. So, so this has been work that has been done in recent years. And one of the key assumptions there is that this type of communication structures that we are putting in place, are rather static over time. But that can become a little bit challenging when it comes to realistic applications, because typically communication protocols are distance-based, and when you start getting into more complicated real-world situations, you can end up having conditions like this, where the fact that the multi-robot system now needs to navigate in a narrow environment is not possible because of the constraints due to the network robustness through fixed communication. So in a paper that actually appeared this morning at ICRA, we show our recent work on how you can maintain the same level of robustness while allowing dynamic network topology. And the way of doing that is that you can check the stronger robustness conditions with algorithms from the literature. You can take that condition, make it a control barrier function, a safety filter, and have a desired performance like the one that you showed in this video. To see that also in hardware implementation, this is the same case studies, but also implemented with our crazy flies. And in order to signify the resilient consensus, that consensus is being achieved, we show that with consensus on the LED colors that the robots are emitting. So the leaders are emitting blue colors, but there are also malicious leaders that are emitting red color. Eventually, all the followers, since we are on a resilient network, converge to emitting the same blue color that is the nominal signal that they were supposed to emit. This has been, a very quick keynote on some of our work on network resilience. I would like now to focus on some aspects of our work that focus on the safety of the network from the perspective of the safety of the individual agents against physical attackers and other type of disturbances such as moving obstacles. So along with another student that recently graduated, we have also looked into this problem of swarms versus swarms. What can you do when you have an attacking swarm that's trying to go to an area that's supposed not to be at, and you want to employ a defending swarm of robots so that they are able to herd them away? And so this problem would involve then the developing of an architecture from the very, very high level task assignment problem of how you are allocating defending robots against the attacking swarm, against attacker robots, and how they can replan and reallocate for the case that the attacking swarm might be breaking into multiple directions in a way to overwhelm the defense. And we have developed the planning and the control and sufficient conditions under which this herding and intercept can be successful, upon, of course, assumptions on the knowledge of the models and so on. Moving a little bit to environments where it's not necessarily adversarial, but rather just dynamic obstacles in the space, we have developed this type of safe coordination algorithms, again, using the notion of control barrier functions and extended into multi-robot implementations. And the idea is that then in these decentralized formulations, the robots take into account the neighbors that are nearby, and they're able to safely navigate to their respective goals while avoiding collisions. Now, this is a deterministic setting from the perspective of we know the model, essentially the behavior model of the others within a horizon down in the future, which again could be less realistic for certain applications. One of them is social navigation, where the model of the surrounding environment can be more complicated. So you need the proper stochastic modeling for your system. And the control barrier function now needs to be formed in a probabilistic sense with a proper notions of risk. So in our recent work that has been submitted to ICRA, what we are doing here is that this risk threshold that you're willing to take, we just allow it to adapt. We are allowing it to adapt so that agents can can become riskier as long as they do not exceed an upper bounded threshold. And that essentially helps a lot with the feasibility and the performance of the algorithm, which is a big issue on how do you make sure that you always have efficient navigation solutions from the perspective of always being able to find a solution that avoids deadlocks. So empirically, we have shown that our method really here helps with the performance of the algorithm as well. And a last video, when it comes to applications that are more about environmental monitoring and monitoring of environments or quantities of interest in the environment, this is an experimental implementation of in our Fly Lab with only 2 robots, but the algorithm scaled to any type of robots. Where now safety here is in terms of not just collision avoidance, but also in terms of guaranteeing remaining energy budgets for the robots. So the robots are guaranteed to go and explore and collect data from the environmental from the parts of the environmental that are unknown, and they can do that while always making sure that they will make it on time to their charging station, so that at least no one essentially runs out of battery life while they're still operating. And with that, that's my last slide. I would like to acknowledge the support of our sponsors, and of course, my students who have been doing all this great work. So thank you very much for your attention.
Thank you very much, Dimitra. We do have time for 2 quick questions. Is there a question? We have mics. Yes, there is a question over there.
Hello.
How about this side of the room? It seems like the other side is much more engaged. Can we also get a question from this side of the room? Please go ahead.
Very cool talk. I was curious how you measure the propagation of information through swarms. Is it some form of mutual information or directed information?
In the first part of the talk, that was a classical, rather, broadcast protocol where the leader is broadcasting information to the followers, and depending on the architecture, the followers could be broadcasting information to lower layers of the architecture. And the objective is to achieve resilient consensus to the nominal leader's signal. So that would be the application implementation in the first part of the talk.
And one more question.
Yep.
Do you see any potential for studying self-replication in swarms to ensure physical resilience?
How would you find physical resilience?
Well, you were speaking of defending from an attacking swarm,
Yeah.
but perhaps if one or two, multiple agents become disabled, how to ensure self-replication or to repair the broken drones?
So we haven't really integrated yet both the cyber aspect of resilience and the physical aspect of resilience, but that's our ongoing work right now and our next goal. How to make sure that they will be able to operate within a secure network, and when faults happen on the physical level, they will be able to figure out what to do, if that's answer your questions. Yeah.
Yeah, actually, that's a very interesting scenario. But I see that the left side of the auditorium is engaged. So I'll come back to that. But first, let's hear from.
Hi, my name is Harshit. I'm from Drexel University. So my question was, in one of the examples that you mentioned, the leader was malefic and was sending negative signals, which would hit the wall, which would make the swarm disengage into the wall. So my question is, when the leader sends out the message, is it the followers that are taking the decision? Is it like a decentralized swarm decision that's going on, or?
Yes, the decision is being done by each one of the of the followers, and what enables the decision to be secure is that every follower has essentially a resilience verification check. Do I receive the same message, the same identical message, or within some bounds that correspond to noise levels and so on, from at least F+1 incoming connections? If that is true, then you can show that if your malicious agents are up to F, then essentially you know that you're going to discard a bad message, or you will receive enough good copies to know that indeed this is a legitimate message now. This is how it works. So it is decentralized in that sense.
Thank you
Dimitra,
so much.
I think that's all we have time for,
Yeah.
and I will find you after to
Yes,
talk about
absolutely.
physical failures and reliability, especially in the energy case where each robot might carry important information.
Exactly,
And so
yeah.
how would you deal with someone detecting, I'm about to fail, how do I help the rest of the team with what I know? So, okay, let's give Dimitra another big round of applause. Thank you, Dimitra.